Everyone, I'm Jimmy Zelinskie. This is a talk on running low latency workloads on Kubernetes. This talk I have is actually split into two sections. The first section is going to be around designing the software that you're going to be ultimately running on Kubernetes. And the second one is actually going to be about operationalizing and what it takes to kind of take that software and run it on top of Kubernetes using the Kubernetes primitives in the most efficient way. This presentation is content that is largely derived from our own personal journey developing software at auth primarily SpiceDB, which is an open source project I'll get into in the future. I'm one of the co-founders of auth and one of the creators of SpiceDB. I previously worked at CoreOS, which was an early kind of cloud native ecosystem pioneer. We are kind of famous for building etcd, which is the data store that Kubernetes uses under the hood, alongside kind of being the third largest contributor to Kubernetes behind Google and Red Hat before it was acquired, ultimately by Red Hat. So I worked on a bunch of stuff in that ecosystem. I'm a maintainer of OCI, which is actually the standard for containers, and I contributed a bunch and created some of the foundational CNCF technologies. I have contact information here. I'm honestly best reached by email. And if you have any questions, or don't hesitate to reach out to me. I'm a pretty personal guy. But before we can talk about low latency systems, we have to kind of level set on what type of low latency we're talking about. Low latency can mean a lot of different things to a lot of different people. Front-end developers, they have a different idea of what their latency window is when compared to someone like a database developer or game developers or even embedded systems developers. So before we get talking, first we have to establish what window we're talking about. So we're definitely talking about network services. In the theme of this conference, there's a lot of different database systems being spoken about. So what we're really primarily interested in here is these type of network services that probably are targeting latency requirements around single-digit milliseconds, or possibly even one millisecond or sub-millisecond performance. We're not talking about the kind of software ecosystem around soft and hard real-time systems. That is ultimately a completely different ecosystem, and I don't want to get into that today. The type of systems I want to get into today are ones that are running in garbage collected languages and running on the cloud. So I kind of have these two examples on this slide. We have a pacemaker. This literally has people's lives in your hand based on the performance and kind of interactions you're having. We are not talking about that. We are not taking anyone's lives into our hands, but we are talking about software that could be making real-time trading on the market, the financial markets, which maybe is also putting people's lives in your hand, right? Because you could definitely lose a whole bunch of money very quickly. But as I mentioned before, our experience is largely driven by the development of a project called SpiceDB. For those unfamiliar, SpiceDB is a database system, but it's purpose-built around storing and querying data for authorization. So this project is written in a garbage collected language, Go, and it is totally open source Apache 2 license. It's inspired actually by the internal system for authorization used at Google. If you remember Google+, this is the thing that actually drove Google+ circles. And the ultimate idea behind SpiceDB is that you can take your authorization data and logic and centralize it into one service where you can allocate a team to manage that, where they can enforce the best practices, correctness. It can be the source of truth for authorization and access across your entire organization, across a suite of microservices, across your product portfolio. And then you can also, by centralizing that, guarantee that the proper disaster recovery and robustness is applied to that particular environment because it is critical. Great. So that is the reason why you would want to use SpiceDB. We also kind of have an example of queries here, just so you can kind of visualize in your mind's eye what type of things you ask SpiceDB. So the most basic thing you can ask is a permissions check. Can a subject take a particular action on a resource? But because SpiceDB is a database, we can do all kinds of clever things, like actually find you all of the subjects that can take an action on a particular resource, or we can give you all the resources a particular subject can take an action on. And SpiceDB is a really interesting use case because it actually has very low latency requirements because permission checks usually take place before you can actually do any of the other work. Before you actually reach out to your relational database to fetch the data, you first need to check whether a user can actually list that data and see that data. So we're talking about targeting milliseconds, way smaller than actually what you're going to take to reach out over the network to a service like RDS or your MySQL instance, right? The other major thing here is if we give a correct answer or an inconsistent answer, that is a security vulnerability because you gave access to someone that should not have access to a thing. So not only does the system have to be low latency, but it also has to be correct and correct at a scale across your whole organization. So just how far does this scale? A few years ago, we actually scaled to observe some performance in a real customer environment. And we scaled up to 1 million QPS. This is the point at which we ran out of IP addresses in Google Cloud. Common story if you ever tried to do large scale benchmarking in any cloud provider. But what we observed at the 1 million QPS was 5 milliseconds at the P95. I know this is P99 conf, but I can share with you the P95. We do have this blog post where you can find our P99 at a bunch of different observed kind of intervals of scale from that testing. So the question on everyone's mind now is, how do you design for this type of low latency system? I joke here, but in reality, I think that this is very true. Basically, you want to write the most understandable software possible, and then you profile to test your assumptions. If you're not familiar, profiling is basically a way of sampling where time is spent in real running systems. So you're always going to follow this loop where you're going to hypothesize about a change that's going to impact performance. Then you're going to test it and benchmark it locally on your own machine or in your CI/CD process. And then you're going to deploy it into a production environment and you're going to profile it to see where reality actually meets it. Because benchmarks will never be a real customer environment, a real world environment. And you can't just rely on pure kind of algorithmic intuition as to whether or not something is going to be faster or not. Reality will smack you in the face. So there's two incredibly useful types of profiles that you can use, basically concurrency ones and memory ones. And that's because these are the most powerful abstractions or lies the computer is giving you. The concurrency lie is that the language you're working with or the operating system you're working with is convincing you that a single core can do more than one thing at a time. So you're going to have to build a bunch of different abstractions in your programming language of choice, even something like Go. We've had to build higher level concurrency patterns to make sure that we're doing things correctly here and really using the system to its full potential. SpiceDB has C star that kind of is giving them the same framework for this. But then you're going to have to build these kind of controls over it as well, where you can set limits, cancel things once they're no longer relevant, and prioritize things so that if there's a particular task that is not critical, it cannot block any of the critical tasks that are being performed by the system. The second kind of abstraction and lie the computer is giving you is that if you're using a garbage collected language, it's pretending you have unlimited memory. You can just continue to allocate memory and you never have to clean up after yourself because that's the garbage collector's job. This is great, but it can definitely be unwieldy. And I think that you are totally fine to use a garbage collected language for these performance critical workloads, so long as the language allows for some amount of control over when allocations take place. Go is one of those languages where it's very intuitive when you're allocating and when you aren't, and it has static analysis tools to help you figure that out. But in addition to that, you're also going to need to be able to kind of tune the GC based on your workload to make sure, because there's always a trade-off in garbage collected languages between latency and throughput. So to kind of tackle that first level of concurrency, SpiceDB does a bunch of different things, but the high level strategy is that you need to parallelize as much as possible. So the idea that we have is basically inspired by the reality of kind of processor design. CPUs aren't getting as fast as they used to. Dennard scaling is kind of falling over. So instead, nowadays, what we have to deal with is having just more and more dense CPUs where there are more cores. So that means we fundamentally have to take our problems and divide and conquer them across a set of cores, but not only a set of cores for an individual machine, but also for a deployment across like a whole cluster environment. So you're going to network across a bunch of different machines. So SpiceDB does this by actually self-clustering when you deploy it on Kubernetes. So it discovers other pods that are deployed in the same deployment. And then it will actually shard up work across them. And we actually kind of break down requests into sub requests that are assigned to a particular pod. And the interesting thing about that is it's actually all structural. So if you have two different requests that share some of the underlying computation, they will actually be able to reuse the same work being done on the cluster. Super powerful ideas. All just facilitated by the fact that you have to parallelize everything. So to do that, you definitely need to be able to have a task system where you can control things by priority. The most powerful abstraction I think you get here is a thing that we call single flight, which is basically function called deduplication. The idea behind this is if you make a request and there's a particular thing, particular hot spot where a whole bunch of people want that same information, the second person that comes making that same request is actually going to wait. They're not going to perform the duplicate work. And then when that first person, his result comes back, you use that to serve both the first person and the second person. Believe me, this just drops latency and you can just use this everywhere. Second up is hedging requests. Hedging requests is kind of a double-edged sword. This is the idea that if you actually want to duplicate all work, on the off chance that the first guy fails, you need the second guy already running and doing that work because you can't wait the whole period for the first guy to fail, plus then the overhead of computing the thing a second time. That will not fit into your latency window. This is really, really tricky because you also have to scale up the cluster and deal with a lot of the prioritization in your task system to actually make this kind of work in the right way. So you really, really need to experiment with hedging requests before you just start applying it across your system. Next up is kind of putting everything in memory. Like we're trying to tackle the memory profiles now. That means you're probably going to have to write your own data structures. We were really lucky and were able to reuse some of the implementations of the core data structure in SpiceDB, which is called TinyLFU, that were written in the Go ecosystem. So we didn't have to do this, but we have submitted patches and helped to fix that and maintain that over time. So you want to keep as much in memory in a cache as possible. But if you cannot do that, the next thing that happens, you better be ready to reach out over the network. Like everything else is teed up. So what we end up doing is we have connections already pooled and maxed and established, because even doing something like a TLS handshake to establish a new connection is enough to blow some of these SLAs. So that means every connection has to be ready to be used if you're going to reach out over the network the second it gets taken off the shelf. The next thing is working with your garbage collector. So setting go mem limit is the example I give here. This is what tells the garbage collector how much memory it's working with. That lets it defer a lot of work until there actually is a lot of pressure and it really is reaching its limits. The trick here is actually that you're going to be working in environments, probably in containers, where what the system is reporting and what the container has allocated are going to differ. So you really need to be careful that you're setting these values correctly. The most powerful thing you can do in a garbage collector language is actually reusing buffers. So if you do make an allocation, which is the most expensive thing you can do, you better be able to reuse that perpetually. So you use things like buffer pools to reuse them. And if you start making pull requests in your language ecosystem to other libraries that people are using, sometimes you can squeeze out 100x performance increases in things. Most recently, there is actually a bunch of work by LinkedIn improving the gRPC implementation in Go, really focused around raising buffers, and it has made drastic performance improvements for everyone using Go. Finally, just simplifying as much as possible, your garbage collector might be able to actually skip a whole bunch of work that it has to do if it knows that there aren't any pointers in a giant map that you have allocated in memory. Perhaps all of your data in memory is actually stored inside of a map. If you have any pointer types within that, that means it has to iterate over that whole map trying to see if any of those pointers are dead. If you use really basic types like integers, it can just look at the type of the map and skip the whole thing. Cool. So we've got all that. Now we can focus on actually running a low latency system. So if you're interested, all of Zed's products run on Kubernetes. And I actually have given a previous talk for the CNCF at this URL. So you can go here after the fact and watch that and learn more about that. But the point here is that actually running these systems on Kubernetes is not easy. If you paid attention to my bio at the beginning, been in the Kubernetes ecosystem since before Kubernetes existed. So very, very familiar with Kubernetes. None of the stuff was obvious to us, and it was all lessons learned once we went to deploy these systems in a real-time fashion. So I like to think of the Kubernetes defaults as your Linksys router. It's got something that kind of works. I mean, they used to just say admin, but now they give you kind of like this random string on a sticker. If you check your Wi-Fi list, you'll see all these. You know people are using them, and it probably works good enough for them. But there's a lot of problems with this. In Kubernetes, the defaults, they're not going to protect you from anything consuming too much of the resources on a single node. So nothing stops actually one pod from consuming all the memory and killing and hurting all the performance of every other pod on that node. And there's actually nothing preventing it from scheduling two of the same type of workload on the same node. So that means you could lose a node and actually lose two replicas, which might actually cause a really, really big outage depending on the type of workload you're deploying. So the obvious thing is to just give the scheduler more details. So chains and tolerations are one of those primitives. The general concept here is affinity and anti-affinity. Basically, you say this type of node can only handle this type of pod, and then that lets you create invariants like only deploy one of this pod on a particular node, or you can actually even create a separate pool that will uniquely be hardware specialized for that workload. That's super powerful. Great starting place. This is what everyone will tell you if you just Google it or check Stack Overflow. They say just set requests and limits, right? So requests basically say this is how much memory or CPU this pod needs, and limits say this is where like the maximum is. Don't let anything go beyond this. So we're done. We just set that, right? Well, the reality is there's pros and cons to doing this. You're not going to get killed by the kernel anymore. Instead, you're going to get killed by Kubernetes, which at least picks the right process. So that's a little bit better. It does make performance predictable, but it does come at the cost of some overhead. You're actually not going to be hitting the same performance as if that was like actually like a pure like hardware like VM with that specific kind of hardware allocation. The other thing here is it artificially limits processing. It's a double-edged sword. Previously, you could have had workloads burst and use unused space on that node, but those things could burst to hurt your latency critical workload, but also your latency critical workload could burst to use that extra resource. So maybe not great, but it is a trade-off nonetheless. The other thing here, and probably the most important, is that the limits themselves are reactive. So that means there's a polling rate where Kubernetes is checking in to see if something is acting outside of its boundaries. The problem is if you're running a low latency system, you're probably serving thousands and thousands of requests in that window of time where it's doing that check, all of which those requests can be impacted by that like nefarious pod on the same node. So really, this isn't good enough. And there's no way to actually configure this to a low enough window where it is theoretically good enough. Limits would have to be proactive. And then finally, because there's multiple things running on the same hardware, you suffer from context switching, which I can give a brief aside, just explaining that really quickly. In context switching, basically the idea is there's two different ways that you can do kind of running multiple things on a computer at once. Parallelism, where two things run at the same time completely independently. Then concurrency, where you actually are stopping and swapping in between two different workloads on the same core. There is two different types of kind of events that trigger this. One that is called preemptive scheduling, which is you've just spent too much time running, so I'm going to try to keep things fair and manage the amount of time each thing runs. And then cooperative scheduling, which is a particular event triggers this, like I'm waiting on a syscall, so I can put you to sleep while we're waiting. This has a ton of downstream effects. like invalidating the cache and slowing everything down. Obviously, it's stopping your work to do some other work that may not be as critical. But the important thing to note here is that there's kind of three layers to this. There's the Go programming language doing context switching, then it's context switching across threads that the Linux kernel is then context switching across the hardware CPUs. And actually, even the hardware CPUs often have hardware threads. And those hardware threads are actually an abstraction if you have hyperthreading enabled over one particular core. So there's just layers and layers of this context switching that can all bite you, and you just need to control it as much as possible. So Kubernetes has one last feature, which is the static CPU manager. The static CPU manager basically lets you pin your pods to a particular core, but it does so statically. So the real problem here is like, how are we going to make things dynamic again now that we've pinned them? And that's where Carpenter comes in. There's auto scaling as a feature in Kubernetes, but it is a kind of third-party thing that AWS built, and now it's actually been rehomed into the CNCF. Notably, Azure actually replaced their autoscaler with Carpenter, and I hope that Google will do the same in the future. But this basically will allocate a new VM for you when you need it and when it's requested, when you need to scale up. So this helps you add that dynamic layer back to what was previously made static by using the static CPU manager. So in summary, if there's one takeaway from this talk, controlling the different layers and the different systems and understanding how they're isolated from each other and the requirements they impose on the other layers is critical to understanding latency and guaranteeing it in a particular environment. You need to be aware of the place where you're operating and how you interact with it, although you may not actually, it might be totally opaque to you. And that's the real tricky thing here. I think that these isolation models are so important that we actually put it inside our docs and product marketing material around our database because we believe so firmly that that is the requirement for building low latency systems. So with that, I'd like to shout out the team at Auth who did a bunch of this work. And then if you want to learn more about Kubernetes primitives, this is the best blog post that I could find on it that can go in depth to a level that is a bit more than I wanted to give in this presentation. I'd like to thank P99 CONF for organizing. And if you want to reach out, you can join the SpiceDB Discord. So, thanks.